You are currently the only person in this conference.
Welcome. So this is the lecture 7 and the last of this course. And also this lecture is divided into 2 units. Let's say that this is mainly dedicated to application of magnetism towards spintronics. So let's say a sort of electronics that would like to employ the spin of the electron instead of the charge to transport information. And this will be the topic of the second unit, of the second part. In this first part, we do something which is, let's say, in a certain sense, preliminary, and also has to do with, let's say, fabrication of magnetic sensor and other kind of applications. And in a sense, it's also the continuation of the, let's say, analysis, overview of effects that are physical effects, physical phenomena, in this case, the electrical resistance, that are connected with the magnetic state. So there is a quite large amount of phenomena that involve electrical resistance, magnetic field, and magnetization. And all these effects, they go under a name, which is magnetoresistance. That is a quite a general name for all these effects where the resistance of a metal, a composite, a multi-layer, a bilayer, we will see different kinds of arrangements, depend on the magnetic state. And with magnetic, we mean both magnetization, so orientation of the magnetization, for example, with respect to the current, or magnetic field. Let's start with the first slide in order that we start to subdivide 3 different phenomena. We have a magnetoresistance that is a characteristic of metals. So metals, conductors. In conductors, the resistance depends on the applied magnetic field. This effect, this phenomenon, which is in a sense related to the Hall effect of metals or semiconductors, is called ordinary magnetoresistance. So it's also interesting to look at the names because they can be confusing. Then we have the anisotropic magnetoresistance. So remember that every time you see anisotropic magnetoresistance, you have to immediately associate this with ferromagnets. So the first is the typical magnetoresistance of metals, and the second is the typical magnetoresistance of ferromagnet. Anisotropic means essentially that now you have to specify the direction of the current and the direction of the magnetization. While for the ordinary one, you also have the direction of the field. But we will see that in the first approximation, the resistance depends only on the amplitude of the field. And then we will see exceptions in this. The third effect that I called here scattering, SD scattering ferromagnet, has to do with a completely different effect that is called giant magnetoresistance. This is a quite famous effect because the discovery of this giant magnetoresistance was awarded by the Nobel Prize in 2007. And this effect, let's say, has to do not with single material, but with interfaces between different materials that could be, in all cases, ferromagnets. So it has to do with the fact that the resistivity may change if along their path, their diffusing path, electrons find magnetization vectors pointing in different directions. So we will make, in this first hour, a small review of the ideas and somehow also of the material displaying this effect, and in a few cases also evidence a few applications. That is, let's say, especially in the past, it is the anisotropic magnetoresistance that was used to make magnetic sensors, so sensors of the magnetic field. Now, giant magnetoresistance is applied in a lot of application of spintronics, but let's say that here we will see just the basis, and in the next unit with Michaela, you will see possible application of this giant magnetoresistance effects. So what we will try to do here is to distinguish the causes of these three different kinds of magnetoresistive effects. Let's start at the beginning by saying just a word on electrical conductivity. So we have to spend a very brief and also naive, let's say, describe a quite naive approach of how metals conduct electricity. So why do we have the conduction of electricity? What causes the resistivity or the conductivity of a material? Well, we know that in metals, we have a lot of free electrons. And these electrons essentially obey the Fermi statistics. So they are arranged in what they are called energy bands. And for metal, we know that the Fermi level, so the filling of this energy band, fills within one of these bands. So at the Fermi level, where we can excite, for example, moving electrons, we have a lot of possible carriers. And this makes a difference with respect to semiconductors, where you have very, very few carriers for doped semiconductor, or you have essentially no carriers, just thermal excited carriers between the valence band and the conduction band. Here we are in the middle of the conduction band. So why normal metals are not superconductors? We have a lot of electrons that can freely move in the material. So what causes the finite conductivity of a material? This is essentially due to the fact that if we apply a force, so an electric field, a gradient of electric field, a voltage to your conductor, you cause the shift of the electrons in a certain direction. So you, in a certain sense, you force them to be out of equilibrium. Spontaneously, they would diffuse. So they would go in one direction, then change direction. They will occupy the equilibrium distribution. But if you force in one direction, you will have a diffusive motion. By the way, the diffusive velocity is much smaller than the velocity of the electron themselves. That is often called the Fermi velocity. What caused the finite conductivity is the fact that after a certain travel in space, that is called the mean free path, electrons scatter, so they change direction. And in this change of direction, they dissipate energy. So the equation that you see here at the right-hand side essentially says that conductivity depends, apart from the elementary charge square, on n, the number of electrons, let's say for unit volume or for atom or whatever, something which is quite large. So, the Fermi velocity, and below we have the Fermi velocity, which is quite large number. Then we have what is called the effective mass, that depends on the shape of the band. But for certain bands, for certain band of metals also, it can be almost equal to the mass of the electrons. But then you have this multiplied by this length, which is called the mean free path, that dominates the resistivity. So inside the mean free path, we have all the causes of scattering for the electrons. So, for example, why we should have scattering? We should have scattering, for example, because there are defects in the material. Or, for example, because the lattice is not perfect. You have grain boundaries, so you have defect again. Or again, the lattice is not perfect because you are at a finite temperature. And then the lattice, it's not steady. It moves, it oscillates. So it contains phonon oscillations. These phonons cause scattering. So inside lambda, we have put everything essentially. So all the causes of scattering of this electron. Lambda will change a lot with temperature, will change a lot with microstructure, will change a lot with so many things. While the rest, elementary charge and the Fermi velocity, the mass of the electron, essentially is due to the fact that we have chosen copper, or rather we have chosen aluminium or iron, so something which is related to the crystal, to the element, so something which is intrinsic. Rather, lambda is an extrinsic parameter. So it depends, for example, on microstructure, well, on temperature because of these phonons, and so on and so on. This is important to say because now, if we want to investigate what is the influence of magnetic field, or rather magnetization, we will have to understand where this magnetic effect goes, if it goes into lambda or if it goes into the intrinsic parameters. And we already do expect that lambda is most probably the most affected parameter. So if we change, because the others essentially they depend on the material you choose, and in most of the cases the magnetic field and the magnetization, apart from very small things like magnetostriction, they do not change the crystal structure, they do not change the band structure. This remains the same. But the lambda, the mean free path, can be actually affected by the magnetic field and the magnetization. And now we try to explain how. Well, a lot of things have been understood by making a lot of experiments. So most of the knowledge we have on this joint effect, it's like for the magnetostriction and the magnetocaloric effect. You take material and then you perform measurement. So, for example, what happens to the resistivity of a metal when you apply a magnetic field? This is called, as we said, the ordinary magnetoresistance of metal. If you see the picture at the left, you see a plot where there is the change in resistivity with an applied magnetic field. And at the bottom here, you see a scale in where you have the applied magnetic field, then multiplied by a ratio between the resistivity at high temperature, so at the Debye temperature essentially, over the resistivity at zero temperature. This is put just there in order to normalize the different behavior and to be able to plot all these different elements in the same graph. So you see a lot of elements. These are the metals of these elements, and you see iron, indium, sodium, platinum, gold, bismuth, antimonium, and so on and so on. So the curves are all different, but they share one common thing. If you look, this is log-log scale. So in log-log scale, they very much look linear, this behavior. And if you put the behavior, which is field square, you find that most, apart from very small deviations, most of the known metals, they have a resistivity that is changing with the square of the field. So ordinary magnetoresistance is, in a sense, a small effect. It depends on field square. It exists in most of them, and can have, for sure, a coefficient in front of the field square that depends on the kind of metal, of crystal structure. But as we saw in the previous slide, if we make the hypothesis that the field is not changing the band structure, then the field will change the mean free path. If the resistivity is large, it means that the mean free path is small. If the resistivity is small, it means that the mean free path is large. How can the field change the mean free path. In the picture at the right-hand side, you see a very naive, but in the end, not too wrong explanation. The magnetic field has an important effect on the motion of electrons, and this is the Lorentz force. So if we apply, well, here we're applying an electric field, which is trying to shift electrons in one direction. In the picture that is there is direction X. But then you put a magnetic field in the Z direction, so perpendicular to the screen. What happens is that electron involved in the conduction will feel this magnetic field and will try to follow a sort of cyclotron orbits. So they will change direction because of the presence of the field. The field, it makes no work. So it will not make electron going faster or slower. It will not change their energy, but it will change their direction. So we will try to bend them. As a very, very first approximation, at least in the cartoon shown there, you see that if there is a change in direction, the effective mean free path in the direction of the electric field you have applied is shorter. So it's reasonable that when you have a magnetic field applied, all electrons that are going perpendicularly to it are affected to this field. And then they have a mean free path which is somehow shorter. It's a small effect and it depends just on the square of the field. So ordinary magnetoresistance is something that has been very much investigated in the past. So it also tells a lot about the, let's say, the band structure of the material. So it's very much investigated, but it's not very much used for any application. At least as far as I know, it's not. It's the Hall effect of metal that can be used to make magnetic field sensor. And then in this case, you have to select materials with a very large Hall effect. And these are semiconductors, these are not metals. What kind of other effects? Well, okay, and this is just the first order effect. Then there exist materials where you see an isotropic effect, as you do expect, because you are applying a magnetic field in a direction. I mean, the magnetic field is a vector, and also the electric current is a vector. So you also expect that this change in the mean free path would not be the same if you apply the magnetic field parallel to the current or perpendicular to the current. And these are the three cases that you can do if you study the conductivity in a thin film, for example. And here you have the case of bismuth. The bismuth is a material where, let's say, Hall effect and magnetoresistance effects are important as a metal. And so what do you find? You find that if you put a magnetic field that is, let's say, laboratory scale, so or at least even permanent, even electromagnet, you would not discover anything. So the resistivity will change as the square of the field. But then people took materials and then tried to apply very large magnetic field. So as we have seen, typical fields generated by an electromagnet with an iron yoke, it can be around 2.5 Tesla. Here we go 10 times more, so 25 Tesla. You need very special setup in order to apply this magnetic field. These are not common at all. But if you do that, then you discover that it's not the same applying the field in the direction perpendicular or parallel to the current. And what is very much different is if the field is parallel to the current or it is perpendicular. If you follow the sketch that we have seen before, that is, the magnetic field creates a cyclotron orbit for the electrons, then you immediately associate the larger effect when the field is perpendicular to the current, not parallel. When it's parallel, you expect that it's not affected much. As you see, this is only the case when the fields are very, very large. Otherwise, it goes as we have predicted at the beginning. It's not that immediate to explain this effect here, but in a sense, this is reasonable. So it's reasonable to expect that the mean free path is decreased only when the field is perpendicular to the current. And again, this you find for very large field and you find for metals. Now the question is this true also for ferromagnets, where you change the magnetization direction? In ferromagnets, if you take a ferromagnetic material and you apply a magnetic field and you measure the resistivity, then you find the result, the experimental result of the picture here. So take two different situations. Again, very often you take a thin film as a magnetic material, and then you can orient the magnetization parallel to the current or transverse, that is perpendicular to the current. Let's leave out the case where the magnetization points out of the plane. You measure the resistivity as a function of the applied field, and you discover that for ferromagnets, the behavior is exactly the opposite with respect to bismuth. So, when the magnetization and the electric current is parallel, you find a large resistivity, that is a small mean free path. When the magnetization is perpendicular, the mean free path is large and the resistivity is smaller. Exactly the opposite. So this is quite puzzling because it means that you cannot associate, you cannot say that the magnetization, so the order in the ferromagnetic material is playing the same role of a magnetic field. They are completely different things because the behavior of magnetoresistance is exactly the opposite. It has nothing to do with metals. So the conduction in a ferromagnet is very, very much different from the conduction in a metal, because otherwise you would not find something like this. By the way, if we forget for the moment about the cause, we can look at the amplitude of the effect. 2.5% is not that bad, so it's already something that is reasonably measurable. And look at the material used here. It's an alloy, is essentially nickel with a little bit of cobalt. And we know that nickel is essentially a soft magnetic material. So the orientation of the magnetization between parallel and transverse direction can be done with a very small field. So if there is a change in the resistivity, this could be a method to, instead of making or measuring the magnetization by using magnetometric method or vibrating sample magnetometer or whatever you like, or looking at the domains as we have seen, you could put electric contact, measure the resistivity, and then from the measurement of the resistivity, discover where the magnetization is. And if this is a soft magnetic material, so the magnetization is oriented in the direction of the field, this is also a method to measure the field. So suppose that you make your nickel cobalt material very soft. Then you apply a magnetic field and the magnetization will orient in the same direction of the field. Then you measure the resistivity and you discover the direction of the field. So you have made an electronic compass, something which is very interesting and very useful, because why not to have magnetic sensors that are able to measure the direction or even the amplitude of the magnetic field so easily? How to do that? Well, if we want to make a sensor, then we need not only to know the resistivity as a function of the direction parallel or perpendicular to the direction of the current, but we have to change the angle. And if we change the angle, we discover that the behavior of the resistivity as a function of the angle, it goes like cosine-like behavior. So look at here. Here we have the resistivity as a function of the angle formed by the magnetization with the current. The resistivity, we said, is maximum when the angle is zero, they are parallel, and is minimum when they are perpendicular by half. If we would like to use this as a sensor for the field, or whatever, in any case, this effect is nonlinear. It's nonlinear because you have the cosine. But if you have the cosine, there is one precise point, which is pi divided by 4, where it's approximately linear. So if you want to build a linear sensor, you need to go at an angle of the magnetization that is exactly 45 degrees with respect to the current. So imagine you would like to put the current in direction x, the magnetization in this direction, and then measure the field, because essentially with the field you will change a little bit the orientation of the magnetization, so a little bit more parallel to the current or a little bit more perpendicular. If you do it like this, then you really exploit this effect as a sensor of the magnetic field. How to do this? It's not easy to have the magnetization at 45 degrees. If we, for example, have to make a thin films or have a conductor. There is a very smart solution for this. The solution is sketched here at the bottom. The solution is called the Barber-Pole AMR field sensor. This is something you find around. You find because this AMR field sensor have been the most successful magnetic field sensor for decades. Now there is something, let's say, more technologically, let's say, new, which is based on giant magnetic resistance. But this one was a sensor of magnetic field that probably you still find, but you would have found in any application where you have to sense a small magnetic field. So the read head of a magnetic hard disk of 10 years ago or 20 years ago, it was exactly like this. In ABS for the car, when you control the velocity of the wheels, you have a part of your transmission system that contains a ring which is magnetized, and then there is a magnetic field sensor that counts or measures the velocity by measuring the field. And this sensor is an AMR field sensor. So in so many technological applications in industry, AMR field sensors have been extremely successful and, let's say, one of the most used. Barber pole. Why barber pole? Because if you look at the sign of a barber, at least in the USA, but also probably still in Italy also we have something like this. You have these two colors and this, let's say, bars, no? So the idea was the following. If we want to have the magnetization oriented in one direction and the current at 45 degrees perpendicular, you could devise a system like this. So consider a thin ferromagnetic film, which is very long in one direction. So we have seen that who dominates the energy is magnetostatics. So take this this is a kind of permalloy, this nickel, because you could also put some iron and get very similar effects. So it's very, very soft magnetic material. As I told you, permalloy is one of the alloy which is used to make thin films because it has vanishing zero magnetostriction. So a long bar like this. very thin because it's a deposited film. Then, if it is very long, then the magnetization will tend to stay aligned in this direction here. Because this minimizes magnetostatics. But then, how can I have a current flow at 45 degrees with respect to the magnetization? So the trick is to put above the magnetic thin films these slides of metal that are put at 45 degrees. Then what happens if you apply if you let a current pass through this system here? Well, the current will mainly go through the metal, but then in order to pass from one to the other, it has to go into the ferromagnet. And then we have exactly the situation that we wanted. The current would flow at 45 degrees because it's the minimum distance between the two slides. And we have really the condition that we wanted. This is the barber pole AMR sensor. So very tricky, very nice as a way to exploit a region where the behavior of this anisotropic magnetoresistance is linear. So even if it was not completely understood why anisotropic magnetoresistance is such that, people has immediately started to think about building a device. So if you put a magnetic field, because as the magnetization is oriented to one in this direction here, if you put a small magnetic field perpendicular, the magnetization will start to bend up and down, and then the resistivity change. And this you detect very easily because it's quite easy to measure a change of a few percent of resistivity. Now, let's make a step beyond in a certain sense, because as we notice, we cannot apply ideas of electrical conductivity that we use for metals also to ferromagnets, because we discovered that we were not able absolutely to get any, I mean, we got the opposite effect. If we just use the Lorentz force, for example, for a ferromagnet, the opposite effect of that we expect for the anisotropic magnetoresistance. So we have to go a little bit more in detail if we want to understand something of the conductivity of metals. But in general, we have to go a little bit more in detail on the conductivity of metals. Why? Well, because we know that not all metals are good conductors. We have noble metals, copper, silver, that are very good conductors. Other materials that are alkali metals, they're not very much used because they are too reactive, but they are also very good conductors. But there are others, elemental material of the transition metal, that are non-ferromagnetic and are not very good conductors. Vanadium, zirconium, they conduct very bad electricity. And the same is for ferromagnets. If you take the resistivity of typical ferromagnets, they do not conduct electricity very well. But why? This is a general behavior. So independently if they are ferromagnetic or not, we have then to distinguish between them. If you take transition metals, for example, you discover one thing, is that at the beginning of the series where you have sodium and cesium, you have electrons, you have to look at the energy bands. So if you take at the beginning, the only electrons, they fill the S band. So bands that are completely symmetrical and then that are quite wide, so their span in energy is very large, and they are generally filled up to a certain level, let's say half filled, for example. Then when you put more electrons, so you follow the periodic table and you have more and more electrons available, then what you do, you fill the d band, but at a certain point, if you fill the d band completely, you arrive at a certain point that it corresponds to the noble metal, where the d band is completely field. And then again, you have at the Fermi level only the S band. These are the noble metals. Everything what is in between, the level of feeling, the Fermi level, is in some way also crossing the d band. So at the Fermi level, you have both S electrons with a very wide band in energy, and the d band that has energy, has a width that is much, much more smaller. Small band means also a very large equivalent mass. So what do we have, for example, for the 3D metals? We have that as electrons are very mobile, they contribute to the conduction of electricity. The d electrons are very localized. In the language of conductivity, you can say that they have a very large equivalent mass. So they contribute to electricity very little. They are almost, let's say, localized, almost. So if the density of state, which is what you find here, is very large, it means that the band is similar to an energy level. While if the band is wide in energy, like this, so the density is very small, it resembles very little an energy level. Their electrons are completely spread. They can go whatever they want. So there is an association with large density of states and localization. The d electrons are very much localized. This explains why vanadium, zirconium, and many elements of the middle of the transition metals, they do not conduct electricity very well. Because you have the superposition of the S and D. But you could ask, why the presence of more electrons makes the resistivity larger? Because you could say, I mean, more electrons, more conduction, but this is not the case. Why? And this is a quantum effect that we see in the next slide. This is because most of the electrons, they will scatter, the S electrons, they will scatter in the d band. So they will very often leave the very mobile state in order to occupy states that are in the very localized state of the d band. So if you have only S state at the Fermi level, this means much better conduction. If you have the Fermi level that is crossing the d states, then the conduction is very bad, because it creates a scattering between the S electrons and the d electrons. The characteristic of ferromagnetic metals is that the two d band are split in energy, because we have ferromagnetic order. And the ferromagnetic order is mainly due to the d electrons. These d electrons, they not only, let's say, in one of the conduction energy bands, but they are also responsible for ferromagnetism. And so, if we have spontaneous magnetization, it means that one of the energy bands, it's called the majority one, has a lower energy. If you sum up the spin or the magnetic moment of the up band and the down band, it doesn't give to zero. It doesn't give zero. It gives the spontaneous magnetization. So up electrons, majority, and down electrons, minority, are energy split. What happens? So if you use the same idea that we use for the transition metal at the left here, then it means that certain kind of electrons up, let's say, so in the same direction of the magnetization, they conduct electricity well. The other, the down, no, they conduct bad. So in ferromagnetic material, you have two parallel conduction, one for up electrons and one for down electrons. And this superposition creates the specific properties of ferromagnets. You have different, for example, mean free paths for up electrons and down electrons. Let's change slide. The idea in order to describe this was by Neville Motz, so an Englishman that probably also got a Nobel Prize for a few of his research. Now I'm not sure of this. He's quite famous for many things, but one of the things is the so-called two currents model that exactly states the idea that I mentioned before. Two currents model is based on this idea. Why can we consider up electrons and down electrons as a parallel, let's say, in the conductivity? Because following Motz, he said, well, electrons change direction every mean-free path, so every lambda, but they do not very often change spin. So they can change the direction where they diffuse, but before they change their direction, they go from one magnetization spin up or magnetization up or magnetization down. They can scatter, for example, 100 times, because the mechanism that contributes to the change in the direction and the mechanism that contribute to the spin flip is completely different. One is related to the defect. The other, as we will see later, is related to the spin-orbit interaction. And this may be very much different. So in many cases, you may have this, that the spin diffusion length is much more larger than the mean free path. We have introduced another important thing, the fact that the electrons can scatter several times, but they conserve their spin. And sometimes they change at random, for example. So they go into other subband. If we take copper, no, where 2b and up spin or in the down spin is the same thing. And we discover something, that there is a coherency for the spin. The spin diffusion length, the numbers that I put there, they came from some kind of evaluation of copper, of these materials. The spin diffusion length is evaluated around 200 nanometers, a lot, while the mean free path for copper could be around 20 nanometers. So you cannot have an electron coherent traveling more than 20, but that the same electron can travel for 200 nanometers before reversing the spin. And so this allows, in a certain sense, to take this diffusion length as it's much larger than the mean free path, as essentially to say that for the conduction, you may consider that the up electrons and down electrons act independently. So you may just sum up the two sub-band as an electrical parallel. This is for copper, where spin diffusion length is very large and the mean free path for up and down is the same. But for ferromagnets, as we said, the mean path for up and down is not the same. It's different. There is a subband where you do have very little sources for the scattering, because the Fermi level lies completely in the S-band. And so they travel, they diffuse, and the MF free path has a certain value. But if after a certain spin diffusion length they change spin, then the mean free path is completely different. It's much smaller. So this is a typical conduction for a ferromagnet. Here the Motz model still apply. If you measure the spin diffusion length for nickel, is much more smaller than for copper, but is still much larger than both mean free path for up and down. So again, you're allowed to consider the two up and down bands as independent. So it's an electrical parallel, but the conductivity of the up is much larger, where for the down electrons, they continuously scatter. The mean free path is extremely small. So you need to reverse again the spin in order to contribute to the conduction of electricity. This is a characteristic of ferromagnets. The fact of having a different mean-free path for electrons with a magnetization, with a spin, I mean, a local magnetization parallel to the main magnetization or anti-parallel. And this creates the specific things of ferromagnets. Oh, again, this is very bad. This is very bad because you cannot see the slides. I don't understand why sometimes this happens. So let's see if I can share the screen and show you the right one. Okay, so for a moment you will see my screen. Yes, and you will see, I hope, the right slide. Okay, that should be like that. But I think this is a problem of the program we use slideshow. So in the PDF you will find all correct. Okay, so how Motz devised to make this hypothesis of having current in parallel for ferromagnetic materials? Well, the idea also came because if you take materials with a band structure which is very similar, so for example, nickel and palladium, well, for nickel, we know that system is not always ferromagnetic. If you go above the Curie temperature, you go into the paramagnetic state. So you do expect, I mean, there will be no spontaneous magnetization, and the two band will be much more similar to the one of metals. But we said, if between palladium and nickel, I mean, the two bands are, let's say, similar, why we not just rescale? Well, take the resistivity as a function of temperature for both materials. Take the temperature region above the Curie point, and then just rescale the two resistivity as a function of temperature of nickel and palladium in order to go together. And then we look at what happens at below the Curie temperature of nickel. What happens is what you find here. If you let the two curves to go together here, then when the nickel becomes ferromagnetic, then the resistivity drops down. The resistivity drops down in the sense that, and here it's justified the fact that for palladium, both bands, they still are able to conduct electricity, but they are both bands, they conduct bad because in both for the upspin and for the downspin, you have the scattering due to the 3D band, where you have the Fermi level crossing. In nickel, when you go down in temperature and then it becomes ferromagnetic, at a certain point, the D bands for the up electrons will go below the Fermi level. So for the up band, you will have no more D electrons at the Fermi level. And this means that the majority electrons with magnetization up will have very small resistivity. And this is the value that is here. So the resistivity, it doesn't increase, it goes down. It conducts better when it's ferromagnetic because in one of the subband, you have the good conditions, while for palladium, you never have. So when you go ferromagnetic, you have the possibility to have a better conductivity because one of the subband can go in a condition where you have no more these d electrons that decrease the mean free path. Let's go back to the main screen. Okay, I think we are again here. And let's proceed. There are measure values for the mean free path of majority and minority electrons. These are all given in nanometer. So, for example, aluminum, copper, they are not magnetic. The lambda S, the spin diffusion length, is in both cases much more larger than the mean free path, and the mean free path are those shown there. For iron, there's quite contradicting data, so it's not clear if we have a real difference, because iron is a material where the Fermi level lies on the d band for both majority and minority spin. For cobalt and nickel, the situation is more clear. We have the mean free path, which is much more larger for the majority one, and also for the iron-nickel alloys. So those materials in which the d band for the majority electrons is completely below the Fermi level are called strong ferromagnets. Strong, it doesn't mean that they are particularly large magnetization. That is not the case. Nickel is an example of a strong ferromagnet. Cobalt, so and so, as far as I know. Okay, let's go on, because starting from this idea, then you may understand that if you make a synthetic material in which you can possibly change the direction of the magnetization, I mean, you have many layers, ferromagnetic layers separated by non-magnetic layers. And then you are able, in a certain way, to pass from a condition where, if you look at the ferromagnetic layers, they are anti-parallel or all parallel. And then if you think of the conductivity as we described here, you may wonder that the total conductivity of the material as a whole can be completely different. If the magnetization are all parallel, regardless of the spacer that you can put, let's consider that the spacer are very small, much smaller than the mean free path. Then the up electrons will travel with their intrinsic mean free path, possibly crossing many of the different layers, while the minority spins, they travel exactly at their mean free path that is very small. But if you go in a condition where the layers are alternating, as soon as an electron it finds in the neighboring layers, if it was a majority in the first layer, now it's a minority electron in the other layer. So you have continuously scattering. If you have a situation like this, you have a very large resistivity. With all parallel, you have a very low resistivity. The difference between this value can be very large. And so Albert Fert and Peter Grünberg, who discovered this effect, call this effect as giant magnetoresistance. It's giant because it's much larger than the anisotropic one that was known for ferromagnets. This is the original result of the paper of 1988. They used a multi-layer of iron cobalt, and they used a trick in order to have at zero field a situation where the magnetization is anti-parallel. And then with the applied field, they could orient, and they essentially use an interaction which is called RKKY, to have an antiferromagnetic line interaction between the different layers. But in any case, what is important, and if you look at the change of resistivity, this is really relevant. So the giant magnetoresistance of multi-layer or layers developed a lot, and you will learn in the next hour with me some of the possible applications. So I jump over this because essentially it tells what I've just mentioned here. In this case, you have parallel magnetization, you have always one channel which is favorable, but with antiparallel, no. So it's like you can use this MOTS two-current model, so resistances that are in parallel, to explain this giant magnetic resistance effect. And this was the original interpretation given by Albert Ferb. Let's still add one element, and then we go to the conclusions. The element is what we mentioned at a certain point. We said there is spin-orbit coupling, which is important for electron, also for conduction electron. And this spin-orbit coupling, this is what gives you the strength of the spin flip, the possibility to flip the spins. So, as we learn from the MOTS model, it's not that strong, because otherwise we would have change of spin at every scattering, and this is not the case. So in many cases, this spin-orbit coupling can be negligible. But let's see what it is, first of all. Spin-orbit coupling, it has to do, it can be well described for bound electrons, not for conduction electrons. So we can do this both in a quantum view, but also in a very, let's say, intuitive classical view. If you take, you can either take an electron that has an angular momentum around its nucleus, but you can also make the opposite view, where you fix yourself at the electrons and you look at your nucleus turning around you. This nucleus will correspond to a sort of current, and then this current of a field. And then what does it mean? Is then that the spin of your electron will have a coupling with the magnetic field generated by what you see as a current. This is a classical view, and so it means that between the spin, so the magnetic, something intrinsic to electron, and the orbital motion of this spin, there is a correlation. This correlation, let's say, it favors one of the conditions. This is the condition that is more favorable, the one where the equivalent magnetic moment of the electron and the equivalent field generated by the fact that you turn around the nucleus are in the same direction. So the same magnetic energy we use always. Is this spin-orbit coupling, here we have not time to go too much into the details, is responsible for a wide number of very small effects, let's say. One of these effects is the Hall effect in ferromagnets. Hall effect in ferromagnets that not only if you put a magnetic field, you generate a transverse voltage, but also without any magnetic field, if you have a magnetization that is perpendicular to the current, the Hall effect of ferromagnet can have very different signs. And is something that in the end is related to this small spin-orbit coupling that you may have in ferromagnets. Those that could be interested, there exists a recent review. So even if this is an old effect, it is until recently that it has been a little bit more understood. So there are many specific mechanisms. Anyhow, take this as something to remember that, but let's go on. So this is the important point that we want to mention, because if we said that spin-orbit coupling is also responsible of spin flip, so there could be an influence. If we have a spin diffusion length that is small, it means that spin-orbit coupling is stronger. So we do expect that also the orientation of the magnetization with respect to the current can change. For example, we said if the magnetization is perpendicular to the electric current, we may have a stronger effect of spin orbit. And the stronger effect of spin orbit means a smaller spin diffusion length. So we do not expect all effects, as previously said, but we do expect that the electron spin may change more easily. And this is something that may occur. And this may help to us to understand why do we have anisotropic magnetoresistance. Because it's not any cyclotronic orbit that is generated by the fact that we have magnetization either parallel or transverse, but the fact that in one case, the spin orbit is a little bit stronger for the electron that diffuse in that direction. And then the mean free path is smaller. And the mean free path smaller can be associated with a smaller resistivity. If you want to understand in more detail anisotropic magnetoresistance, there exists this model of Schmidt, where they also make the hypothesis, then as the majority of scattering is due to the minority electrons, those in which the d electrons, the Fermi level is in the middle of the d electrons, then you have another contribution that was discovered by Schmidt, and it's well explained in the book of O'Handley, where you have an enhanced scattering, because exactly when you have the Fermi level in the middle, then the spin-orbit interaction also acts as an increase of scattering probability. So the minority electrons are more and more scattered because of this effect. And with this, we're already at 1 hour, so 10:07, and I have some bibliography here. So let's say that what we have seen in this hour is a quite brief overview. And you find in Book of Magnetism a lot of details, because this is a topic that is, let's say still current research, but at least the base have been discussed in books. So concerning this resistances, most of the material that I've shown I've taken from the book of Coy, Magnetism and Magnetic Material. That is a very nice book. Callity and Graham is a quite old book, Callity, that was now recently, it had a second edition in 2008, so it's quite valid and classical. A lot of material also you find the book of Robert O'Handley, Modern Magnetic Material, Principal Application. Is a little bit old, to 2000, but it's a very good source. So concerning sensors, magnetic field sensor, many things I've taken from the book of Fiorillo, Measurement and Characterization of Magnetic Materials. There is also this, French are always been strong and very active in magnetism. And so this book, Magnetism, Material and Application, collection of contribution from the French community working in magnetism, also very valuable. Very much more specific to fundamental aspect is this very nice and recent book by Storr, more related to the electronic structure. And with this, I stop here. So thank you very much for the attention. And if you have questions, please ask. Or any feedback you would like to give. Okay. Michaela, everything's clear. Thank you, Giuseppe. You encourage me very much, because this is one of the most difficult ones for me, because we go very much, at least for me, a little bit off topic. But as, let's say, can we say 60% of those making research in magnetism are more or less related to this topic, Michaela?
Yeah.
Maybe yes. So there is a lot of attention Even this is just the basis. There is a lot of attention on the topics related to electronic transport and magnetism nowadays. So we try to give at least a couple of hours on this, even if we know that it's strongly incomplete.
So when do we want to start? At 10:25?
Okay, I think it's correct.
Okay.
Okay, so thank you everyone, and you can stop recording. Eh?
Oh yes.
10:25.
And already Vittoria, of course, gave a very nice introduction to this lecture on spintronics. But before starting with spintronics, I would just to make my usual summary of the last lecture on hard magnetic materials. Let's be quick because I don't expect any answers from you. So what is the difference between the pH and MH curve? This we should have learned in the last lecture, of course, because this is very important for hard magnetic materials. So this does not have much to do with soft magnetic materials, but for hard magnetic materials, we have, of course, a difference in coercivity, and this should be considered. What is the main application of hard magnetic materials? So hard magnetic materials, of course, you know, are used as a field source. What is the load line and the working point? So this we discussed quite in details. So the load line defines the working point, defines the point where you're working in your application. So you're usually not working in the remanence exactly, but in the working point. And the load line gives you this point as the crossing point between the load line and the hysteresis curve. What kind of hard magnetic materials do exist? And we distinguished 3 groups of hard magnetic materials, so hard ferrites, rare earth compounds, 3 alloys. And how can hard magnetic materials be measured? And there, of course, we had only to add something more because in lecture on soft magnetic materials, but one of the problems, of course, is to reach high enough fields in order to measure hard magnetic materials. We said we need about 3 times the coercivity in order to reach about more or less saturation. And this can be fields up to 6 or 7 Tesla. So you can, for example, use a pulsed field technique, which goes up to these very high fields. But this is only as an example. But now let's move to our new topic, since we don't want to switch too much topic. This lecture, actually, I always tell to the students, this is not a lecture at all. So this is to give you just a feeling what is research in magnetism nowadays. So in my first lecture, I told you that magnetism was studied already 4,000 years ago by humankind, and we are still studying it, and we are still doing research, and I think this is very interesting. And this is just to show you what actually we are doing and in which direction magnetism is developing. And spintronics is actually one of the, let's say, one of the topics which are evolving very, very quickly. So it's very difficult to teach you something on that. But at least we would like to show you what is going on. So what is electronics? Of course, we said already, this gives us really the hope to develop a new kind of electronics. Again, electronics which is not based on charge currents, but which is based on so-called spin currents. So where information in electronics is not transported by charge, but it's transported by spins. And of course, one can very easily imagine a spin polarized current. So if electrons are all spin polarized, then you will also transport spin, of course. But in this lecture, I would like also to show you that we would like to go beyond this concept. So the concept of spin polarized currents is a concept that is used already in the GMR, as you saw by Vittoria, where you polarize electrons. And in this way, you can have new effects, and that's very interesting already. But if we could further, let's say, separate the two concepts, charge and spin, then we could reach applications which have really very big advantages. So we would like to go towards pure spin currents, and we will immediately see why we go towards pure spin currents. Although this concept might be a little bit strange for you, because thinking about an electron which divides charge and spin, how can it be possible? It's not possible, of course. So this is just to show you here the publications per year when you search in the web for the word spintronics. This word was invented, let's say, around 2000, so at the beginning of this century. And you see there's a rapid increase in the last 20 years on publications on spintronics. And all this, I already mentioned, came from the fact that a new kind of electronic is kind of urgent, let's say, because the semiconductor industry already for several years, of course, is looking for new paradigms, because due to the limitation of the Moore law, we have to go into new directions. And so spintronics was created by the semiconductor research community. And there was a great interest, of course, of electronics industry. But what is the main advantage of this spintronics? Why do we want to go towards pure spin currents? So where charge and spin are separated, and information is only transported by the spin, let's say. And the main reason, of course, is Joule heat. So always when you have charges moving, then you have Joule heat, and you have a lot of waste heat and wasted energy. And of course, everybody who has a graphics card at home knows that the graphics cards are relatively big and make a lot of noise. And that's only because they have these large fans, because they are heating up so much. And of course, this is only energy that is wasted. So if we could find an electronics based on the spins, then we could most probably lower the power consumption a lot. But there might be also other advantages. For example, electronics based on spins might be faster and even more sensitive, and we might see some applications in this lecture. On the other hand, I have to tell you, to be honest, that still, let's say, concerning this new kind of electronics, we are not so far at the moment in research. So very often when you move into research projects, then you will hear about this technology readiness level. And you can see here the first 3 levels that are mentioned. So the first level would be basic principles observed. The second, technology concept formulated. And the third, experimental proof of concept. And nowadays, let's say we reach this experimental proof of concept. So in spintronics, most of the studies that we are doing are at TRL 3, and they try to be developed further. So they should go now to 4 or 5, of course, in the next years. But there's still a bit of work to do, let's say. So spintronics is also interesting from another point of view, because it's really a multidisciplinary approach, and it involves a lot of different topics and research groups, let's say. For example, here you can see material science. We have several topics that are touched from material science side, and also from nanoscience, but also from fundamental physics. All this goes together, of course, with a metrological approach. So we are a metrology institute, and you may wonder, so what's doing metrology in the field of spintronics? But spintronics, of course, needs also metrology, because measurements in spintronics are of a very big importance. Accurate measurements, not only production of materials, but also measuring this kind of materials is really important. And we saw in the last years, so we performed, for example, in the field of spintronics, 2 different kind of round robins, and we saw that this is still a very open point, and measurement accuracy is very difficult to reach, even if we compare one single sample with the same measurement method in different labs. We cannot reach very comparable results at the moment, and that's, of course, a very critical point, because if you want to go towards industrial applications, how can you do that if you have no measurement standards available at the moment? So spintronics started with the semiconductor community, but moved very quickly towards the magnetism community, and there it really found a very fertile ground. And nowadays, as Vittorio told you, many researchers in magnetism are working in spintronics, and this was already pushed very much by the finding of the GMR, and especially by the award of the Nobel Prize in 2007. And of course, Vittoria already told you exactly what is the GMR. No, we saw this in details from a theoretical point of view, but from application point of view, and this maybe caused the fact that it was awarded with the Nobel Prize, is that we have a very important application. And of course, I also said this in my introduction, the first lecture, and this is the read head sensor of the hard disk. So, because this really created an incredible improvement of hard disks and the storage density that we can reach, because we have nowadays GMR sensors which are much more sensitive than the old one AMR sensors, which were based on AMR, as you saw in this lecture today. So this industrial impact, of course, caused the fame, let's say, of this effect. And this is just this slide here to show you how much we improved from the first hard disks. Nowadays, in the first lecture, I showed you this very tiny external hard disk that I had, which is going up to 2 or 3 terabytes. And here you can see the first hard disk in 1957, developed by IBM. It's called TRaMM. And it consisted of 52 disks of 60 centimeters diameter, and the storage capacity was 3.75 megabyte. So this is makes us almost laugh, let's say, on this really big device. As you can see here, it's 1 meter high. You could store more or less one photo that you could make with your cell phone today. So that's really, and give a look to this video. It's really a nice video if you can access YouTube, because it shows you from where's coming this invention of the disk, and why the disks were considered to be more convenient, because at that time people use the magnetic tapes mainly for storing, which still people are doing. So instead now we have this bit size of 10 to 100 nanometers. And what I always like to mention here is that the scanning distance of the read head above the magnetic film is about 5 to 10 nanometers. So I really think that this is really impressive, because you need a mechanics that is very well stabilized in order to do that. And that's not easy. And that's also one of the disadvantages, let's say, of hard disks and of magnetic recording, because the mechanics has to be really very sophisticated nowadays. You need, of course, these scanning distances in order to read the very small signals of your small bit areas. And this is again the picture that I showed you already in my first lecture, where you can see how much the storage density increased with the invention of the GMR. And then this increase moved on with the perpendicular recording. So these are very important developments. Nowadays, of course, we are moving more and more to flash hard disks. Everybody who has a laptop at home knows that most of them has SSD hard disks in the computer, and we don't use anymore, maybe also for these reasons, for the problem of mechanics, magnetic recording. However, we should not forget that magnetic recording is not dead at all, and it's still used a lot in big cloud centers, because if you want to store, however, your information, your memory for a long time, then you need stable devices, and flash is not considered stable enough, let's say, and that's why in very big cloud centers they still use tapes, magnetic tapes. Okay, spintronics is not only magnetic recording, as you can see here, but it consists of several other parts, let's say, and possible technological developments. And one of them we will see in this lecture is the MRAM. So it's a kind of magnetic memory, which is very easily integrable in CMOS devices, and can be coupled to processors. Then we might have a new kind of ICT, let's say, based on excitations of magnetization configurations, which are spin waves, so-called spin waves. And we might have also a new kind of electronics and logic, all based on spin and not on charge. And this shows really the great technological potential of spintronics. We divide spintronics also in several subtopics, let's say, although all of them are always coupled by spin current. So spin current always plays a very big role in all the subtopics of spintronics, of course. And you can see here magnonics. So this would be, let's say, spin transport by spin waves, so by these excitations of magnetization configurations. Then we could have spin caloritronics, and I will show you this briefly because our group was working quite a lot on this. This is concerns the interaction between spin currents and thermal currents. And of course, spin torque and magnetization dynamics, this is the basic ingredient also for GMR and for all kinds of effects related to GMR. And then we have, as let's say, lately the most important topic, spin orbitronics. So this is everything that has to do with spin orbit coupling. So spin orbit coupling, of course, is very important in this field. And I also mentioned when we spoke about spin-orbit coupling that spin-orbit coupling may lead to non-collinear alignment of spins and may lead to very certain structures like these skyrmions here, magnetization structures, and they have completely different properties with respect, of course, to traditional magnetic structures. And with these new properties, you can develop very new kind of applications. Spin-orbitronics is also related to the spin-hole effect, and this is the effect nowadays to reveal spin currents, so the inverse of the spin-hole effect, and we will also see this effect at the end of the lecture. So now let's summarize very quickly what was shown already by there's not so much to, of course, almost nothing, I would say, but I would like to summarize and give you a slightly different point of view. So this first slide is just to again emphasize the difference between the different magnetoresistance effects. So Vittorio already said that GMR has nothing to do in principle with the other two kind of magnetoresistance effects. So the classical magnetoresistance effect is happens in all metallic materials, of course, and it's simply caused by the Lorentz force. In magnetic materials, instead, we have the same effect, but it becomes the anisotropic magnetoresistance due to the fact that we have magnetization in the material. And as the field acts on the electrons in a metal, in a non-magnetic material, let's say, the magnetization also acts on the electrons, as it would be a field, of course. In this case, you saw also that the angle between the magnetization and the current counts. So this is an important fact. And you can see in the two different directions, parallel and antiparallel, you will find completely different resistance curves with respect to the magnetic field that you apply. This here is the example of cobalt. This effect is of a few percent, so we find a change in resistance of a few percent, for example, for cobalt, as you can see. And this is completely different to what we find in the giant resistance effect. That's why we were able to increase so much sensitivity of the read head sensor disks, because now the effect is about 50%, not a few percent, let's say. And one of the most important experiments that you see here was done by Beibich in 1988 in order to understand the GMR, was the experiment of the iron-chromium multilayers and to measure resistance in these multilayers. And he found by changing the magnetic field that you might have a change in resistance of up to 50%. And this depends a lot on the thickness of the chromium layer. And this was studied immediately after. So 2 years after, Parkin published this paper here, where he studied the dependence of the resistance change on the thickness of the chromium layer. And you see this very strange oscillating behavior. So we find a minimum resistance change here at 0, then we find a maximum, we go down to a minimum again, and so on, oscillating. And this, of course, stimulated the researchers to think about an oscillating exchange interaction, as we found in the RKKY exchange interaction. So if you remember this RKY exchange interaction, it tells you that we have an exchange that is oscillating from ferromagnetic to antiferromagnetic with the distance between the two localized magnetic moments. So this was an exchange that was transported from between two localized magnetic moments by free electrons, let's say. So it was somehow clear that there must be something very similar to this RKKY mechanism behind. And instead of the localized magnetic moments, we had now two magnetic layers, the two iron layers, the non-magnetic layer in between. And what counts is now the direction of the magnetization of the two different layers. So they act as if they were two localized magnetic moments, let's say in the RKKY interaction. So the angle between the two magnetization counts here, and this was studied by DNE in 1991. So if we have parallel configuration, then we will have delta rho is equal to 0. And if we have anti-parallel, we will have delta rho is maximum. So we have maximum resistance in the anti-parallel configuration, while we have minimum in the parallel configuration. Of course, the origin of this GMR you can find and you can describe in the SD model, for example, as Vittorio showed you. And the theory can be rather complex, but I think it's still nice to remember that we have already an ingredient from the lectures that we did in order to understand the GMR. And this comes from the Stoner model, where we said in the Stoner model, we might have, not the Stoner model, if you remember, this was the exchange interaction, and let's say this was ferromagnetism in itinerant systems. So in order to understand how free electrons, in a free electron system, you can get spontaneous magnetization. And this is due to the fact we have the Pauli principle. So we said due to Pauli principle, electrons with opposite spins can get much closer than electrons with the same spin. But if they get closer, then they will feel a much stronger Coulomb repulsion. So you have a stronger scattering between electrons, let's say, if they have the spins antiparallel. And this causes you an increase of energy. And sometimes it's more convenient to shift the part of spin up electrons to the spin down electrons, as you can see here plotted for this density of states, for example. And you get an energetically preferred situation. And this was the Stoner ferromagnetism. So with this principle, however, that the Coulomb repulsion is stronger for electrons with opposite spins, we immediately understand that there must be some kind of spin-dependent scattering. So scattering is stronger for electrons with opposite spins. And having this in mind, now we can understand, of course, this three-layer structure that we need to have a GMR. So we need to have two ferromagnetic layers and a non-magnetic layer in between. If they are magnetized parallel, then we have, of course, electrons that are passing through these layers with a certain spin. Let's assume it parallel to the direction of the magnetization. And this electron will always pass in both of the ferromagnetic layers. On the other hand, we can have the opposite spin, and this electron will always be scattered at both of the ferromagnetic layers. Now let's take the other situation. Anti-ferromagnetic situation. So we have anti-parallel alignment between the two ferromagnetic layers. let's consider the first electron. It will pass the upper layer, but it will be scattered at the bottom layer. The opposite spin direction, of course, is just the other way around. It will pass the bottom layer and it will be scattered at the top layer. So in this way, we always have a scattering. In this way, we have one spin channel that will always pass. So this will necessarily bring you a low resistance state, while this necessarily will bring you a higher resistance state. So just to mention one thing more, now we think here about electrons that are passing in the vertical direction here through these layers. So this would be the direction of the current, but we could think about electrons that are passing in the horizontal direction in these layers. And of course, the effect would be the same. And in fact, we usually prepare our sensors that are based on GMR in this way, with the so-called current in plane situation. Because the current perpendicular to plane situation is not that easy to realize, because you have to think about that these layers here are very thin. They are a few nanometers thin. So overall, the resistance of 3 layers of a few nanometers is very, very low. And so also the resistance change is very low. And in order to measure that, it's not that easy. So we prefer to go to this current in plane situation. Maybe it creates a little bit more difficulties to imagine how these effects still work, but of course you have to consider that the electron, and Vittorio showed you this very clearly, now does not pass through these layers in a straight line and goes through. It always changes direction, and you will have a scattering at the interface, especially because these layers are really thin. And this is another very important ingredient, that these layers are so thin, because otherwise all these effects would not work. They are based, however, on the interface between the different layers and not on the bulk. These effects would never work in bulk materials. So I put here this note. Now the interface layer thickness should be smaller than the spin diffusion length. This is the main point. No? Otherwise, if we lose spin information while the electrons are passing through this interface layer, then the effect cannot work at all. And you saw already some numbers of the spin diffusion lengths and also of the mean free path. And here again, I put something to remind you, just to tell you that all this could be studied only once nanotechnology was developed at a certain point. Because, of course, in macroscopic wise, you could never have found this kind of effects. Once we developed so far the nanotechnologies in order to prepare thin films for GMR, of course, these effects could be studied. So a nice way to describe this difference in resistance is the two-current model, and also that was already mentioned in the lecture before. So we consider the two spin channels as a parallel of, it's an electrical parallel, simple. And we have a spin up and spin down. If you consider here your two layers with a parallel configuration, and we have these two types of resistances. So of course here R1 would refer to a parallel configuration. R2 would refer to an anti-parallel configuration. So R2 will be always larger than R1. And in the antiferromagnetic situation, anti-parallel situation, we have the both resistances here mixed. We have on one spin channel always both resistances. If then we calculate simply the parallel of these electrical circuits, we find immediately that the resistance of the ferromagnetic state with respect to the antiferromagnetic state or antiparallel state, of course, has to be smaller. So this immediately describes us what we found also experimentally. So moving now to the application of the GMR, the main application nowadays are field sensors, as it is the case in the read head, but also in many other applications nowadays, GMR are substituting the old AMR sensors. Field sensors are used a lot in technological applications, and having this possibility to introduce a more sensitive sensor, of course, is very important. So this is the typical structure of a so-called spin valve as it is used in a field sensor based on GMR. And again, we have our two ferromagnetic layers and the non-magnetic layer between. This first ferromagnetic layer here, we usually call it fixed layer because it serves, let's say, in order to polarize the electrons that are coming from the current. And therefore, the magnetization has to be fixed in a certain direction. How can you fix the magnetization in a certain direction? One of the easiest way that you could think about, of course, might be anisotropy. You can think about magnetocrystalline anisotropy, which could be in plane in a certain direction, but you could also think about shape anisotropy. So, for example, you could have an ellipsoidal structure. If you consider that these are nanostructures, they can be patterned, for example, in certain shapes. Another very elegant way is to put below the ferromagnetic layer an antiferromagnetic layer. The antiferromagnetic layer will not contribute with magnetization because overall magnetization is zero, but you can consider it as having many layers inside which are alternating the magnetization direction. No? So the last layer will point in a certain direction, and this, however, will couple via exchange with the ferromagnetic layer and will impose a certain magnetization direction on the ferromagnetic layer. So this is to fix the fixed ferromagnetic layer. And then on the top, we have a so-called free ferromagnetic layer. So, but why it is free? It is free only because we are so smart to use the thickness of this interface layer, non-magnetic interface layer, in a way now to have this so-called RKKY interaction equal to zero. So I showed you, this RKKY changes from positive exchange to negative exchange, but of course at a certain distance, you will have exactly zero exchange. And this is what we want. We don't want to have exchange between this so-called fixed layer and the free layer. Why? Because your electrons will move through the fixed layer. They will get polarized, which of course, yeah, they will get polarized. But the point is that the free layer has to be free to orient with the magnetic field that we want to measure. Because otherwise, if it would always point in the direction of the field, then you could not measure easily an additional magnetic field that is applied from outside. So if we have no interaction, this free layer will immediately, especially if it's a soft material, as it is indicated here, for example, permalloy, will immediately orient in the direction of the applied magnetic field. Okay, and this is how we realize, of course, our field sensor. Again, you can see here in this paper of DNE in 1991, the result of such a resistance measurement. And we see different situations. Let's say here at negative field, we have the free layer and the fixed layer parallel. Then if we decrease this field, we come to 0, then the free layer will switch, of course. We have an anti-parallel situation, so we have high resistance. Then at a certain point, also the fixed layer will switch and we have again a parallel situation. So we move from a low resistance state to a high resistance state and again a low resistance state. So you can see here that there's some kind of hysteresis in this switching of the fixed layer, because we said this fixed layer is a little bit more hard material. No, it should have some kind of anisotropy. But of course, we also have some hysteresis here for the switching of the free layer, which is around 0. But here in this graph, you can almost not see it because usually use a very, very soft magnetic material. One moved in applications now a bit away from this kappa interface layer, and one moved towards the so-called magnetic tunnel junctions. And I think industrially almost only tunnel junctions are applied anymore and not the classical spin valves. The difference is really tiny. So the difference is only that instead of having the metal layer here between the ferromagnetic layers, you have an insulating layer, or usually this MgO. And in this way, you increase a lot resistance. Of course, in theory, electron could not pass through an insulating layer. But since these layers are very thin, so between 1 or 2 nanometers, electrons can pass through the quantum tunneling effect. So this gives you the possibility to increase the resistivity extremely of this structure, and of course increasing also the resistance change that you will measure when you apply your field sensor. So you can see here that now we have resistance changes of several 100%. And of course, using this in the read heads or in sensors gives you an even more higher sensitivity. Another step that people did is now to use not in-plane magnetization, but to use perpendicular magnetization, because this gives you another advantage, let's say, in dynamics. So since you saw that you might have a switching of magnetization of your ferromagnetic layers, if the dynamics is faster, then this could lead to other kind of applications. And these applications are, for example, these magnetic memories that I mentioned at the beginning. Here we use, let's say, as a single bit, one of these structures, one of these empty J's of these 3 layers is your single bit and can be in a 0, 1 state, which would be the parallel or the anti-parallel configuration of these ferromagnetic layers. So now, in order to read these structures, of course, it's very, very easy with this highly sensitive resistance change. We can sense the direction of the bit, especially of the free layer, of course, and we can read the information on your magnetic random access memory. The problem is how to write on such a memory, of course. Usually on a hard disk, you write the single bit by bringing a small coil close to this bit and change magnetization direction. But this, of course, is again very tricky from a mechanical point of view. If we want to improve our applications, then there should be some more elegant way. And the really very elegant way and crucial step to bring forward these MRAMs was the finding of the spin transfer torque. And this I'll show you in this slide here. And this was found by Berger and Slonchevsky in 1996 independently. And you see here again our three-layer structure with the current that is coming through. And we want to analyze what happens now to these electrons. I already told you when electrons are passing in the fixed layer, they might be polarized. And this is one of the important effects. So if my electron is passing the fixed layer, it gets polarized in the direction of the fixed layer, and then it encounters the free layers. But what happens to the free layer now? So if the free layer would be a fixed layer, the electron would get polarized again, but the free layer is free to move. So there can be a transfer of angular momentum. And this is what happens. So my electrons, which are polarized, will transfer a part of angular momentum, this perpendicular part here, the perpendicular component, to the free layer, and the free layer, as a consequence, since it is very free to move, will align in the direction of the fixed layer. So in this way, we set the free layer parallel to the fixed layer when we push through a DC current. On the other hand, we can change current direction. We come now from the other side with the electrons. The electrons parallel to the fixed layer will move through, and the ones anti-parallel will be reflected by the fixed layer and then come back to the free layer. Again, we transfer the perpendicular component, and what happens is that the free layer will switch. So we will set the free layer anti-parallel with respect to the fixed layer. So in this way, very easily, we can write a 0 and a 1 bit in your MRAM memory. So this is really very, very elegant in order to write information on an MRAM. Of course, consider that the currents that we use are very high. You can see here 10 to the 6 amps per square meter. You also have to overcome a certain critical current to write on these structures here. Again, this shows us that all this is only possible because we are using nanotechnology. So we are using nanostructures nowadays. Otherwise, such high current densities we could not push through a macroscopic wire. So let's give a closer look what happens exactly. And we can describe everything again with the torque equation. If you remember the torque equation from the first lectures, it describes the magnetization dynamics of a magnetic moment. In this case, we assume that our body, which is a nanostructure, is uniformly magnetized, and its amplitude, the magnetization amplitude, is constant, and we speak about a so-called macro spin model because the whole structure behaves as if it were only a magnetic moment. Okay, of course, in my field here, I can have several energetical terms, as you remember from the lectures of the energy terms. In the most simple case, for example, you would have the demagnetizing field, and then you can derive from this equation here, of course, the ferromagnetic resonance that we already touched in the lectures. But of course, you can have all kinds of other terms. But then we have to add damping. As you know, the spin system is coupled to the lattice by damping, and in this way we find the Landau-Lifshitz-Gilbert equation, and also that you studied already with Vittorio. If we put it in the Landau-Lifshitz notation, this equation, then you will find very nicely that adding the term for the spin torque, which was found by Berger and Slonczewski, you see that the spin torque term has a really very similar appearance to the damping term. So now the role played by the effective magnetic field is played now by the polarizer, so the fixed layer here, the magnetization of the fixed layer, P. But you see exactly the same shape of this term here. So these two terms act in the same way, let's say, but depending on this constant here, beta, which depends on the current that I apply. So the current, of course, can have several effects. For example, the current can help the damping, or let's say is so small that the damping is still dominant. And this is case one. So damping is dominant and the current is smaller than a critical current. In the case two, we might have exactly damping compensated. And this is a very particular case because it reminds us of the ferromagnetic resonance. So we don't have damping and we have a stable precession of magnetization. And in the third case, we will have a magnetization switching. So what I showed you before, that the magnetization will switch to the opposite state. And this is depicted here, how this switching can occur, for example. Interesting for applications is, for example, the stable magnetization oscillation. As for ferromagnetic resonance, you might have this now only applying a DC current, and this is really nice. You force your magnetization to oscillate stably, and in this way it will produce signals at gigahertz. So you can use this also for ICD. And all this only by a DC current. Now let's move towards the single topics in spintronics. And let's speak 1 second about spin currents, because GMR, as you saw now, is based more or less on spin polarized currents. So all effects are based on the fact that the DC current enters and will get spin polarized. And this amplifies certain effects, let's say, and brings new effects. But if you want to go in the direction of pure spin currents, as I mentioned at the beginning, because this could be more convenient for energetical reasons, not to separate charge from the spin, how can we do that? And one fundamental experiment and also theory was done by Johnson and Silsby in this paper here, as you can see. And you can see here a non-magnetic paramagnetic material, metal, something. And on top, we have these stripes here of ferromagnetic material. And they are connected electrically so that we can inject currents. And you see here, one is called injector, the other is called detector. Again, in these ferromagnetic layers, if they are magnetized in a certain direction, then any current, you can see here any current that we will apply to the injector, for example, will pass through the injector in the paramagnetic material, and this current will be spin polarized again by this ferromagnetic stripe. However, the spin polarized current will go in the direction of where we applied, of course, our voltage. Nevertheless, the electrons will diffuse. And some electrons will diffuse also in the opposite direction towards the ferromagnetic detector here. So here you can see the ferromagnetic detector, which will reveal then the presence of a spin current. So this is a nice way also to measure the spin diffusion length, because of course you have to consider that the distance between the injector and detector still to be smaller than the spin diffusion length. Otherwise, this will not work, because if I lose my spin information in between, then I cannot detect any spin current, of course. All this can be described also from a classical point of view using some thermodynamic theory, and this was done by Johnson and Silsby. And that's why very often in papers related to this first work here, pioneering work, you don't speak about spin currents, but more about magnetization currents, as you can see described here. So this was the concept of a, let's say, pure spin current, no? And in order to reveal spin currents, nowadays the effect that we use is the spin Hall effect. And I would like to show you quickly what is the spin Hall effect. It's really an important effect in spintronics nowadays. Everything was discovered already by two Russian scientists in 1971, and they found in semiconductors a spin polarization at the surface induced by an electrical current. Then the concept was taken up again around 2000 by, and the name was created, let's say, by this paper of Hirsch, but in 2000 the effect was taken up very much in relation to the spintronics. So in a normal Hall effect, you remember, of course, that electrons will be deviated by an electric field due to the Lorentz force, and this might give you a voltage in the perpendicular direction. In the spin Hall effects, electrons will be again deviated, but now according to their spin. So spin up will be deviated in one direction, spin down will be deviated in the opposite direction. Overall, the voltage would be zero, of course, in this case. But if you come with a spin polarized current, then you can measure voltage. So if your current is already spin polarized, all electrons will be deviated in one direction, and you can measure a voltage, and in this way you can measure the presence of a spin current. This effect is basically based on what is called the skew scattering, and what was studied by Mott in the 30s. And it's, let's say, the scattering, the spin-dependent scattering of an electron at an element which has a strong spin-orbit coupling. And so an electron with a certain spin will be scattered in one direction, and an electron with the opposite spin will be scattered in the opposite direction. Of course, in which direction depends on the spin-orbit coupling constant and on the spin-orbit coupling energy. And the spin-orbit coupling energy we discussed in the lecture at the beginning, that depends very much on the derivative of the potential, of the Coulomb potential. So the spin-orbit coupling energy is the stronger, the heavier is the atom, for example. And that's also the reason why we use heavy metals for this spin Hall effect and for revealing spin currents by spin Hall effect. And one of the elements that we use mostly is platinum, for example. So what can we do now that we have the possibility to reveal spin currents? We can reveal spin currents also that are produced in quite particular ways, let's say. And this happens in spin caloritronics, and our group was quite active in this field on spin caloritronics. So spin caloritronics, here you can see this paper of 2008 published by Uchida. It revealed the so-called spin Seebeck effect. So the Seebeck effect, if you remember, is when you have a temperature gradient across a junction of two metals, then you can measure a voltage that is produced by this temperature gradient due to the differences of the Fermi level. Now we should have the same with spins, let's say. And here you can see this structure is made of an of YIG. So it's a ferromagnetic insulator and ferrimagnetic insulator, and on top you have these stripes here of platinum. We apply a temperature gradient or a temperature difference, and we will measure a spin current that is produced due to this temperature gradient and revealed in these platinum stripes due to the inverse spin Hall effect. So unfortunately, this first experiment, although the idea was completely correct, was not performed that well, because it was found then that there are spurious effects like the Nernst effect, which are based on out-of-plane temperature gradients, give more contribution to this voltage that you measure than it is the case in for the spin Seebeck effect. And so one passed then to a different kind of structure, to this longitudinal structure here, where the gradient is applied across, so perpendicular to the structure. And in this way, you find the correct spin Seebeck effect, let's say. So what is the interesting point about this application of spin caloritronics? First of all, we are dealing now with insulators. So YIG is an garnet, it's an insulator, it's an oxide, and you're sure that you don't have any spin polarized current anymore. What you have is a pure spin current. And this pure spin current, now one knows, is based on so-called spin waves, so on these excitations of magnetization configuration. So in this way, you can eliminate Joule heat, first of all, and second, you can find applications, kind of classical applications, for the Seebeck effect or for the Peltier effect, thermoelectric effects, as coolers or generators, for example, which are now prepared with semiconductors in a quite complicated way, because you need kind of pillars here and junctions between P and N doped semiconductors. Now you could prepare it simply with two layers, one of YIG and one of platinum. So the only thing that is still missing is to improve efficiency. And the researchers are working a lot on improving efficiencies of this kind of devices. And this brings us to the next subtopic of spintronics, magnonics. So in YIG, now I told you, you can excite these spin waves also by thermal gradients, and spin waves can be used also for all kinds of electronic applications like logic or filters and so on. And in fact, there is really a huge part dedicated of science in spintronics to developing magnonic devices. And already one is quite far. So what is a spin wave? Just to show it here quickly to you, you can imagine that since your single spin or magnetic moment is precessing, if all spins have a certain phase relation to each other and a certain phase shift, then you get coordinated spin excitations like these spin waves here. If then you go towards the quantum world, then you would call the spin wave simply a magnon. So this would be the difference between spins coupled by exchange, while spin waves, usually we think about spins or magnetic moment, let's say, coupled by magnetostatic fields. Okay, now I already spoke more than 1 hour, so I think I will just tell you the basic principles of the next slides, because it's not necessary to go too much into the details of all these other subtopics that are studied, of course, in spintronics. What is interesting is for what we could use this kind of different topics. And one of them I mentioned already is the magnetic oscillators, and they could be used as microwave generators, for example. So the hope was to create microwave generators just by a DC current, as I showed you before, in the spin valve. And you can use different kind of magnetic structures, for example, this vortex structure here, which would give you different frequency ranges and frequency bands with respect to uniformly magnetized structures. The microwave generator was a bit abandoned, let's say, because there are two basic problems. One is that the power is very low of one nanostructure, and the second one is, in order to get to higher powers, you have to synchronize a lot of structures, many different structures, and synchronizing is not that easy, because in order to produce, because you would need to produce the single elements in a very reproducible way, so that they have resonance frequencies almost exactly the same. Nevertheless, one is coming back to these vortex structures for two reasons. One is what I showed here, the neuromorphic computing. So this is one of the new paradigms, let's say, in computing. And it is hoped that one could use such vortex oscillators as single elements for neuromorphic computing. And the other thing is that since vortex structures, however, have a different dynamic behavior, it's nice to use them also in sensors. So they have improved behavior, especially with respect to noise, with respect to uniformly magnetized structures. So the other important topic is orbitronics. I would say this is the most important topic in the last years. And here we study effects of spin-orbit coupling. And spin-orbit coupling, we mentioned several times, might create a non-collinear alignment of magnetic spins. And this will help you to create not uniformly magnetized structures, but chiral structures. The advantage of such chiral structures, as for example are shown here, these fermions, so these are very strange kind of vortices, let's say, magnetic vortices, is that they have a different magnetic dynamic behavior. and they can be used in dynamic applications, as for example, this racetrack memory. This was already envisioned a long time ago. Here it was thought because in order not to have to scan with your read head over the hard disk, because this is mechanically quite tricky, one could do a different way. One could let the bit move over the sensor. So if you think that here could be your sensor and your bit will move on and will pass the sensor in this way, also you can reveal a series, of course, of bits of up and down. So in order to do this, you would need a wire with several domains that are moving on and domains walls that are passing by. And another way to do this, not with domain walls, could be to do this with the so-called skirmions. Why skirmions? Because skirmions are so-called topologically protected spin structures due to this fact that we have spin-orbit coupling and we have symmetry breaking in the structure. We can create these very stable magnetic structures, which are also faster than domain walls. So they cannot easily be destroyed and they are faster. And this was the great hope to realize finally this racetrack memory, which was a nice idea, something like 15 years ago. And in order to stabilize these structures, non-collinear exchange is of great importance. And if you enter in the field of magnetism, then for sure you will hear speaking about the Chaluzhinsky-Moriya interaction. And this is an perpendicular exchange, let's say, that wants to align your spins perpendicular. And I think with this, we just can stop now here because it's really late and I took more than 1 hour to tell you these things about spintronics. Of course, if you're interested in these topics, okay, here are some references, but of course there's much more scientific literature, let's say, to study in spintronics than books. And if you're interested in these topics, then of course you're welcome to discuss with us and come and see our labs. Of course, maybe I can stop recording and